Hi, good afternoon, everyone. Hopefully you can hear me. We're gonna go through this. Shawn is actually my co-host and he's gonna be online. Hopefully it works. So today we're gonna talk about control of multi-angle color, what's important, what you need to pay attention to when you're working on these kinds of things. So the first thing with this, you need to have digital standards for all your parts or your plants and your part suppliers. You really need to understand the difference in what you're looking at on the vehicle and what angles are actually being measured. The other important thing is our instruments are really only as good as the equations that we use to make the calculations. So I'm going to show you some different calculations that you can use. And then measurement direction for this instrument is key. It's a directional illumination. So if you spin the instrument or do something like that, it's really going to affect your readings. And then finally, Shawn's going to do some reporting and trend analysis. So digital standards, this is why they're so important. In the beginning, you see on the left side, there's different variations between different part suppliers and plants. And if we go to digital standards, then everyone goes to the same center point. So it's much easier for suppliers to match, especially for different locations. The instrument measures the minus 15 through the 110. It also does sparkle characterization and graininess. So here's the geometry of the instrument, and again, it's directional illumination. So we always want to look at where we're measuring on the vehicle, and the most important parts on the vehicle is where, say, the fascias meet the body, because that's a match point, and they're two different materials of the coatings, plus probably two different substrates. So when we look at add-on parts, because you have kind of a slope that's going to be showing you like a different angle perhaps on that part itself, you really want to look at what you're seeing and try to figure out what angle you're looking at. So in this case, we're looking at the 25 or even the 45. And the other part of this is when I'm standing on one side of the vehicle and someone else is standing on the other side, I can think that everything looks great. And the person on the other side can think it's a bad match because we're actually looking at two different angles. So this is, I know like a lot of times everyone stands in kind of like a semicircle. So all the people in the semicircle are looking at different angles on the vehicle. And in this case, I'm looking at the 15 angle and the other person is looking at the 110 angle. So this is really going to change how you evaluate the surface. Here you can see the difference with the numbers. So on the 110, I'm failing. I'm out of spec for the color. But on the 15 angle, I'm in spec. So this is very important, especially for metallic coatings, because the angle you're looking at is really going to affect your judgment. Here's the difference when you're measuring with our instrument. There's two LED lights at the top. Those should be up. And if you're measuring a vertical surface, you always want them up. Two different ways people measure horizontal surfaces. Sometimes they measure with the LEDs towards the glass, and sometimes they do it as it's like traveling down the line. So either way is fine. You just need to be consistent. But on the vertical surfaces, if I spin this instrument, I'm going to get a difference between my two measurements, and it's quite significant. And if I turn it 90 degrees or 180 or 270 degrees, I'm going to get the same type of data, but compared to the other two, it's going to be very different. So we've had customers call and say, there's huge variation between our first and second shifts. And then we'll go actually to the customer and they're measuring one way during the day and a different way at night. And it causes lots of problems. So the instrument does not just measure color, it also measures sparkle and graininess. And sparkle is under direct illumination and graininess is under like a cloudy sky. So this gives us an idea of what flake type, how much the flake that's in there, how it's laying down, if it's correct, many things like that. So for graininess, the high graininess is where you have bigger flakes and they're more separated apart. So you get like a salt and pepper look, and low graininess would be like a fine mica where everything is kind of closer together and you get a lower graininess picture. So sparkle is measured at 3 different angles. The 15 angle is when you're looking straight onto the vehicle, so like the face. The 75 angle is like looking at the flop angle. And the 75 angle really correlates to your process, and the 15 really correlates to your material. So if you have different numbers on the different angles, it's going to give you an idea where you need to look, if it's a material issue or if it's a process issue. Here is how we measure the sparkle. These are not the same as the color angles, so just remember that. We're actually illuminating at the 15, the 45, and the 75, and then we're taking a picture with the camera in the center of the instrument. And then the semicircle is your graininess measurement, and that's diffuse illumination. So sparkle has 2 components. If you just look at your delta sparkle, so your DS number, you're basically looking at a delta E value. So just like with color, you really need to break it down into what direction you're actually going. So sparkle has 2 components, sparkle area and sparkle intensity. Graininess value is 1-dimensional. It goes from 0 to 15. And with both the sparkle and the graininess, we did a lot of visual assessments to figure out, how these numbers would work. And you can visually see a difference in either sparkle or graininess of 0.5. So it's important. Now, we're not going to tell you to pass fail there, but you can definitely see the difference. So these 2 panels, if I just look at the color data, and this is just delta or C-lab numbers, so delta L star, delta A star, delta B star, it's very, very close. When I look at the sparkle numbers, especially on the 15, I'm way higher than just a 0.5 difference. So in the picture, you can see the difference, even though the color numbers aren't giving you that information. We also have combined numbers. Everyone always wants to have one number that says, okay, is this going to pass or fail? Delta E total is all the angles of color that you measure. Delta S total is the sparkle and graininess. And delta SE is sparkle, graininess, and all the color angles in one number. These numbers, because they're rolled up, I would rather have people, if they're going to use these numbers, pass fail on like delta ET and delta ST rather than the delta SE, because the delta SE is very, very diluted number. So it could pass and you really would have either a sparkle or a color problem, and it would dilute that. For Ford, which is who we're doing the study with, at Ford, they use delta E Ford, which is based off the DIN equation, and the components are unweighted. And here's the equation. You don't have to worry about it. All does it in the instrument itself. But this is the equation that Ford uses currently. And we have a new equation that combines the delta E Audi 2000 with the delta E SIE 2000 to give us a new equation called delta E combined. And this equation optimizes for solid, metallics, micas. It also has a tilt in the blue axis to compensate for that, how we see things visually. And it also changes slightly for beiges by making a slight improvement there. So the current delta E Ford is on the left side, and the delta E combined 2 is on the right side. And basically, when we use this new equation, we're almost halving the tolerances. So in this example, space white, the trend is slight green, blue, and really the plant right now is running slightly yellow. So if we make the tolerances tighter on all the angles, it really helps to improve the harmony on that vehicle. So this is what we've been working on. And then on this example, you see the sparkle on the 15 is out of specification. And this one is actually was labeled too sparkly on one of the harmonies, so we know that that's working. And in this case, it would be a material thing. Okay, is Shawn on? There he is.
Is that okay now? Okay, so one thing I want to be stressing on is the fact that what the slide that Ray just showed you there would be the visual assessment of the vehicle, and then basically what we can do numeric visuals or that visual response. Once that's established, along with an equation that supports that numerically, the biggest portion that Ray and I have been talking about is how can we look at large amounts of data within a lot of, some plants may or may not have a robotic cell, or, Ford uses an IPQCS term. It's basically a quality control center with robots that are able to either have film build devices on them, possibly wave scan, or a BIC-Mac. For some people, these cells are very expensive, and so we started doing some collaboration with Fanuc. I know that I'm going to probably be stealing a little bit from, I think, the next presentation, because I know they're going to talk about collaborative robots. But for our use and our use to collect a large amount of data, the fenceless collaborative into it, this solution worked well. So what we're looking at is the ability for this robot to have a BIC-Mac at the end to be able to measure color. We can measure in the exact same location over time. And as Ray had stated, we know that the BIC-Mac will be in the exact same position, so there will be no irregularities between first shift, second shift, operator one, operator two. And then the feature in the robot that doesn't show in the cart portion of the empty area, we have basically we're able to tie in a Rockwell PLC that will give us when the part or what we want to measure is in location. I'll know the body style. So here at the Ford KTPU plant, we have the Navigator, the Expedition. We have a long wheelbase and short wheelbase. So we have different quarter panels that we're going to measure over time. And I'll be able to record the color. So I can interface with that and take a look at that, and then basically be able to empty that data in over time. So Ray, you go to the next slide. This just shows two different devices that we had the capability to put on working with BIC. We could do wave scan in the future if we wanted to go ahead and do some mini wave scan, but we wanted to start with the color. We feel that that was the most important portion because that's what we see outside and that's what impacts our customer the most. So what Ray was talking about with that BIC-Mac robotic, even at the smaller cobot solution, we still have all the effects from our standard handheld BIC-Mac. We still have 5 angle of color measurement. We still have the additional -15 if we want to look at that angle, and we can pull in sparkle and graininess. So all that data is available to us every time we measure. And what we can do is go ahead to the next one, please. Going into here, I just want to bring this back again one more time, is just the functionality of this robot measurement. So what our approach here is at KTPU, just to start working with one of these cobots, we picked one on casters. That way it's functional. This robot actually will plug into a 120 AC outlet. It has a sensor system around that, which as a human can approach it, it will actually slow down. And if you get, I believe, within the work envelope, the robot will stop. So it is collaborative with people on the line. So I could pull this to a film build deck and find a permanent location, or our choice is we are putting it in line. I'm fortunate enough to have a stop station. So at a conveyor spot where we stop, we have roughly 27 to 35 seconds worth of wait time. Our robot movement and scan time roughly is about 17 seconds. So we're predicting that we're going to be able to have 100% capability measurement on all units. So if we are producing 250 to 300 units per shift of the Expedition and Navigator, we should get 100% measurement at a controlled color match point. We have picked the rear fender just because we do a massive part replacement project here. So I want to make sure that what we see in the outside is exactly what we recorded. That way we avoid any panel exchange or anything like that, because the quarter panel is part of the entire body, and therefore that cannot be changed out. So we will not have different data out in the field from what we have measured. Next slide, please. So just some of the outputs that I'd like to talk about, and I know that some people have seen this before, but what we're looking at and being able to chart with this data, first of all, we looked at like an executive or a summary level performance of a color. We went with a box plot style, which would show our delta E on the top, and then you have your L value, A value, B value underneath. What we could do is just be able to look at this. This could be a sheet that's generated for a day's worth of production, a month's worth, you name it. We have the flexibility with the system in order to produce this. So this could be something that a application engineer or a quality manager would be able to print out to take to their bosses, or to a color harmony review or something along those lines to show the performance of that color at an executive level, where they might not understand all the integrate everything there, but they can see that their parts definitely are in spec, or they can see that there's a small spread based on their process capability. Next slide, please. This here, we're looking at a run chart to track color performance. This would be how our process, if you're familiar with run charts, it shows the process trends over time. It's going to allow the engineer, or at a working level with our paint supplier and the engineering team in the paint shops, they can identify patterns of sudden shifts in the process, effective of changes made to the color process. They have an impact. Did we change bell speed? Was there a tint involved? Something that we're predicting a color shift, and we could actually assess, did it work? And we could see how and then also assessment over variation over time, and can show the sources of instability. Remember, and I think right here I said that the scan time is 13 seconds. We do have a 100% measurement. That is what we want to grow into. Unfortunately, I have the cobot located right now on a film build deck, because we are actually removing some equipment for the future spot for that. So right now I can only record to my hard drive, because I am missing a slot for our PLC. And once that vision system comes out, the cobot will go in there and I'll take over, and then it'll be integrated into our plant system. And then finally, next slide, please, Ray. Just some of the benefits of, run track, or taking a look at our process over time. We can look at batch to batch variation within a specific color. So, that will help with our part supplier, or, batch to batch. We can look at the impact of the paint mix room. We can look at, basically with that data over time, we'll be able to see if temperature changes to the mix room or to our paint totes, viscosity, resistivity, material changes. We can look at the application process. Basically did, flow rates, or, a split change. Maybe we went from a 50-50 to a 70-30. We'll be able to track that mean and see if it's an improvement. We can look at the impact of bell speed, shape and error, or high voltage. And then we can also look at the environmental portions of the booth, temperature, humidity. Do we see a shift in a color value? And then we're able to track it to, a shift in temperature or a shift in humidity to the booth. Even something to the oven temperature or oven bake time, did something happen there? And then I also think that we could be able to start to break it down far enough that we could look at the impact of day-to-day production. Maybe it's a high voltage fault, a flow rate or a bell speed fault, or even run stops where maybe another part of the booth, or a position where something else has happened in our paint flow process, where we've held a unit and maybe it got an extended flash, but we still would be able to track back. As I showed you before in the previous slide, even though that's run tracking, and I'm looking at mass data, each one of those will be recorded individually. So if I did see an anomaly, I could break down to that particular, with the FIS capability in our plant, I could break down to that individual unit. I could look at that skid and the time that it went through the booth, and be able to track back if there was a fault, or if there was anything going on in our booth during that time that could have affected that and brought out something that was more of an anomaly across our normal day-to-day production. And then we could also look at equipment changes. There's a lot of stuff out there with spare parts now, and there's a lot of suppliers that are actually kind of coming into their own now, companies like an EFC or that type of thing, that are actually producing their own bell cups, applicators, and different parts that are maybe in the manufacturing world, are something that management might drive us because the part might be cheaper. Could we look at the performance and look at that performance over time and understand that that's not an impact? And then finally, last slide. Next slide. Then we took a stab to see if we were going to be able to look at a control chart per color. This would be after we established a visual acceptance and a numerical value that supports that. And then we could build our limits around there. Currently with the Delta E Ford, we say from 0 to 1 is acceptable. So I've set up just a quick model. This is not real data. I kind of was just playing around. I just wanted to see something that was repeatable. So I put this together, and 0 being perfect to master. So that would be no lower spec limit. But as you can see with the data here, that we were able to actually produce a CPK or a PPK of 5, which is pretty much unheard of. But the thing is, I wanted to prove a point here that we could track CPK or PPK in the manufacturing world to kind of a report to like a management or engineers in the manufacturing world. This is, kind of like a little bit more acceptable with a report. Not everybody can understand color. And when you're maybe talking to production or maybe somebody out in a yard audit or somebody that just wants to understand your process, we do have the capability of taking a snapshot in time and providing them some data on where our capability is. So what we're trying to look at is, can we produce robustly the exact same application process over time, and raise numerical data along with these types of collaborative robots, or the ability to do, repeat measurements, exactly repeat measurements over time, should give us a very good snapshot of where we exist in the color world. Next slide. I believe this is for Rae now.
Do you want me to talk?
We can just say that. Basically, I think what we're both trying to pound the point home is, the more data you collect and the more data that you use is going to ensure that you have a robust color harmony program and a repeatable process in your manufacturing plant.
Okay, so that's the end of the presentation. Do you have any questions?
Like the art question or
Either one.
Easy one. Okay. How do you know which angles represent material versus application? Wouldn't this be different for various colors, materials, applications?
So the only angle I talked about was the sparkle angles, not for color. Color would be different, but for sparkle, the 15 is, I can say 99% of the times that we find the problem, it's a material issue. And on the 75 angle, because that angle is like a flop angle, that's where your flakes are going to be not laying down correctly if you have an application issue. And that's why the Sparkle 75 gives you the information about your process.
Very nice. And are these trend charts available in BYK standard software?
Yes.
Okay.
All the charts, not the last slide that he showed you with all the blue graphs, that is not in our
he made that.
software.
Yeah.
Yeah, but the other stuff is all available, yes.
Okay, so here's a hard one. If I paint something upside down, would I expect to see a different color when the part is then rotated to be put in, vehicle position?
Yes, it could be different.
Yeah.
I know like a lot of the fascia suppliers, they usually paint with their fascias kind of in this position and the ears are on, not in the actual color position. So when we have them measure, we always have them measure like it would be on the vehicle. Because if they measure a different way, it's not going to give the same information that we would take if we were at the plant and the car was in the actual vehicle position.
Yeah, that makes sense. So when you are making a digital standard, are you tweaking those per that color space that it's in so that once it goes to Shawn, then he knows what to do with it?
So all the color equations that we're using in the field now are based off of equations that calculate your tolerancing by where you are in color space. So say I have 100 digital standards for different colors, I only probably have to tweak maybe 5 of them. off of what the actual equations generate. So the equations are way better than they used to be. So it's why we recommend using the newest equation all the time, is because it's really important that you're getting the best data possible. It's going to correlate to what you see visually.
Yeah.
Yeah, and to piggyback off of what Ray is saying there is, the equation that's provided, we do have a typical Delta Ford equation that we use for color. What we're looking to do is making sure that the visual calls that are made out weekly out in our field, or if we're launching a new color and we're working with the design quality team from Ford, where they're coming down and evaluating visually our units and finding an acceptable visual harmony, which is, as we all know, visual is still kind of the key to everything here, is to find a numerical value output that I can record over time that supports that visual assessment, and then to provide the amount of data to show that we are not moving our color position. And then that should enhance our hang-on part suppliers to be able to move into that position to know that we are going to have harmony. So then the numerical data can support what we're seeing visually out in the field.
Are there color spaces that you really like versus one? Is there a color space that you're still, like, we're working on this, or you want
You
would
mean
like
from
to?
the equation perspective, or?
Maybe both.
So the older equations, for mica coats, they gave us some funky answers, and they still do. So that's the newest equations take into account the micas traveling, and sometimes they're a solid color and not a metallic color on an angle. So those are really good for for metallic or mica coats. But nothing really, I mean, it adjusts by where you are in color space. So if it's like a red, it's going to give you not a lot of variation in your hue shift, but you're going to have a lot of variation in your chroma. That's okay. So it adjusts for color space. So I don't see any colors that are an issue.
Okay, that's good. I have another one, and you've sort of answered some of this. How can we address color differences found during a color harmony meeting between the suppliers and the OEM? If the BIC MAC values actually match. So you have a good numeric value, but they're still being called out, during the color harmony review.
So that was kind of the slide when I was talking about the sparkle, when I showed you the two gray panels. So your color data can sometimes be similar between two panels, and you still see a variation on the vehicle itself. And it's usually because of a sparkle, a flake issue, not a color issue per se. So that's why those numbers are really important. I know the industry is kind of realizing that they at least need to collect that data now, but as far as like pass failing on it, not so much yet. But
Right. Okay, very good. Any other comments in the audience? I don't want to miss any of your questions. The app worked really well. Well, this was great. Really great information. Shawn, thanks for joining from Kentucky. We really
Thanks.
appreciate
Hey, I did not realize the impact in the plant for not being able to leave during Derby week.
Yeah.
So
Sounds like
the
fun down there.
Kentucky Derby takes precedence over everything down here.
Yes. Hard to get a hotel room during that week. Well, thank you for joining us. We really appreciate you joining. Thank you, Rae, for presenting as well.
Thank you, everybody.
Thank you.